Tonight we're going to talk about the sky above your head and about a quiet fact that most of us have never been told. That the sky is a farewell in progress, and it has been closing for as long as there has been a sky at all. There is a mountain in the middle of the Pacific Ocean, rising nearly 4¼ kilometers out of the sea, and on its summit there is a scattering of white domes that look, from a distance, like a small colony of sleeping animals. The mountain is called Mauna Kea. Its air is thin and cold and unusually dry, and the sky above it is one of the darkest and most transparent on Earth. 11 countries send astronomers here. The combined light-gathering power of the instruments arranged along its ridge is roughly 15 times that of the Great Palomar Telescope in California, and about 60 times that of the Hubble Space Telescope in its slow orbit above us. If there is a place on the planet where the universe is patiently studied every night, it is here. Imagine tonight one of those astronomers at work. She's inside a dome that turns quietly on old bearings, in a room that smells faintly of electronics and cold metal. Outside, the wind is very soft, and the stars overhead are so numerous that they seem to press down on the mountain like a weight. She has aimed her telescope at a small, unremarkable patch of the constellation Virgo, a patch so faint that no one has ever seen it with the naked eye, and she's gathering on a chill digital sensor the light from a place called Able 2029. Able 2029 is a cluster of galaxies. It sits, by our best measurement, a little over 1 billion light-years away from us, and at its heart is one of the largest galaxies known to exist, an elder called IC 1101, whose halo of stars stretches, by some estimates, across several million light-years of space. The cluster itself is still settling from a collision it suffered with another cluster about 4 billion years ago. Chandra, the great X-ray observatory in high orbit, has taken the deepest X-ray look ever made at this place. It is, in every professional sense of the word, a known and well-studied neighbour. But now consider what the astronomer is actually catching on her sensor. Consider what a photon is, and what it has been doing. Each of the tiny packets of light arriving at her mirror tonight left Able 29 more than 1 billion years ago. It set out across the dark before there were flowers on the earth. It set out before there were forests, before there were fish with jaws, before there were creatures on land at all. It set out, in fact, before the great flowering of complex animal life that we sometimes call the Cambrian, when the seas of our young planet first filled with strange bodies and stranger eyes. That light has been travelling, unbroken and unresting, across the entire long tenure of complex life on Earth. It passed the last of the dinosaurs, it passed the ice ages, it passed the first small mammals stepping out into the warming world, and the first hominids kneeling by rivers, and every human being who has ever looked up at the night sky and wondered what it meant. It has been on its way, patient and unhurried, and it is arriving tonight, on a mountain in Hawaii, into the cold heart of a telescope aimed carefully at where its home used to be. Where its home used to be. That is the phrase that opens the strangeness of this story, and it is the phrase we're going to sit with all night. Because in the time that light was travelling, the universe was expanding. Able 2029 was not sitting still, waiting for its own photons to arrive at Earth. It was receding. It has been receding every day for every day of that billion-year journey, and it is receding still, faster now than when the light set out, and faster still than it will be when the next photon leaves. The picture the astronomer is building on her sensor tonight is not a portrait of Able 2029 as it is. It is a portrait of Able 2029 as it was, long, long ago, sent to us from a place that is no longer where the picture shows it to be. The night sky, for all its steadiness, is not a window into the present universe. It is a record. It is a letter, sealed and posted before we existed, arriving now at an address whose occupants are the descendants of the descendants of the descendants of everything the sender might once have imagined. And here is the quieter thing, the thing that makes this documentary necessary. Some of those senders are already tonight beyond our reach. not merely far from us, in the way distant cities are far. Beyond our reach, in a stricter sense than that, past a boundary in the geometry of space itself, past which no message we send from this mountain tonight, no signal at any speed we know how to make one, could ever catch up to them. And every second, more of them cross that boundary. The sky is a record of things we can see but can never touch, and it is closing while you watch. By the end of tonight, you will understand exactly what that boundary is, and where it lies, and why it exists at all. You will understand what physicists mean when they say that roughly 94 out of every 100 galaxies in the visible sky are already, right now, permanently unreachable, and why the remaining 6% is shrinking with every breath you take. You will understand which few galaxies will stay with the Milky Way for the deep future, which ones are slipping away tonight, and what the sky is going to look like from Earth in the very long run. And you will sit for a while with the small tender fact at the centre of all this, that our era, the era in which we can still see the great cosmic web from horizon to horizon, is a brief and generous chapter in the life of the universe, and we happen to be here to read it. Before we begin, if you love these long quiet journeys as much as we do, a small like or a subscription helps this channel find more curious minds like yours. It is a gentle thing to do, and it means a great deal. Now let us begin. Return first to the astronomer on Mauna Kea, because there is more to the scene than the light coming in. The summit is a difficult place to work. Standing upright too quickly at 4 kilometers of elevation can leave you dizzy for an hour. The air holds less than 2/3 the oxygen of sea level. People move slowly here, and they think slowly, on purpose, because thinking too fast in this air causes small, correctable errors, and small, correctable errors are exactly the kind that ruin a night of data. The mountain has been an observatory since 1964, when the American planetary astronomer Jared Kuiper argued that its combination of dark skies, thin air and stable atmosphere might be one of the best in the world. A 2¼ meter reflector was up and taking data by 1970. Since then, dome after dome has been added, until the ridgeline reads from the air like a row of quiet white shells. Inside one of them the astronomer waits. Her exposure is long, many minutes, because Able 2029 is faint, and light this old arrives at the sensor as a slow drizzle. The dome turns very quietly, keeping the telescope on target as the Earth beneath her rolls. The sensor cools. Numbers accumulate in the memory of a computer that will forward them, at dawn, down the mountain and across an ocean to whichever institution funded the night. She sips water. She checks the weather forecast. She waits. And out beyond the dome, past the atmosphere, past the moon, past the sun, past the outer planets, past the boundary where the solar wind gives way to the interstellar medium, past the nearest stars and the near shore of the Milky Way and its far shore, and the enormous dark between us and the next great galaxy, the light continues to arrive. It has been arriving for a very long time. It set out before our ancestors had faces we would recognize. It set out before our ancestors had ancestors. It set out from a place that has been running away from us, gently but relentlessly, for every moment of its journey. The word to hold, for now, is running. It is not quite the right word, but no word is quite right for what is happening, and running is the word that first suggested itself to the people who noticed. They noticed 100 years ago. They noticed in a small city in northern Arizona, at an observatory built on a mesa above the town. The observatory sits on a place called Mars Hill in Flagstaff, at an elevation of about 2,200 meters. It was founded by the wealthy Boston astronomer Percival Lowell, who had convinced himself for a while that there were canals on Mars, and who wanted a mountaintop of his own from which to prove it. He hired a young man from Indiana, born in the late autumn of 1875 on a farm near a place called Mulberry. The young man was quiet and careful and unusually patient at the eyepiece. His name was Vesto Slipher. Slipher's job at first was not what he became famous for. Lowell wanted spectra of planets. Slipher gave him spectra of planets. But Lowell also wondered about the little smudges of light in the sky that astronomers of the time called spiral nebulae, soft world objects that looked, through a telescope, like pinwheels of milk stirred into black coffee. No one in 1912 knew for certain what they were. Some thought they were clouds of gas within our own galaxy, perhaps solar systems in the process of forming. Others suspected they might be entire other galaxies, unthinkably far away. It was a live and unsettled question. Lowell asked Slipher to point the observatory's 24-inch Clark refractor at these nebulae and gather their light night after night, and let the prism inside his spectrograph spread the light into its colours so that the dark lines of hydrogen and calcium and iron would show themselves. Those lines were the fingerprints. Where those fingerprints sat on the spectrum told you how the object was moving. If a source of light is moving toward you, the waves of its light get squeezed a little as they arrive, and its fingerprint lines slide toward the blue end of the spectrum. If it is moving away from you, the waves are stretched and the lines slide toward the red. This is the Doppler effect, familiar in the change in pitch of a passing train, and by 1912 it was well understood, and Slipher had built himself one of the most sensitive spectrographs in the world for exactly this purpose. He began pointing it at the spirals. The first result from the Great Spiral in Andromeda was a blue shift. Andromeda, as we now know, is one of the very few large things in the universe that is heading in our direction. But the second nebula gave a redshift, and the third, and the fourth. And by 1917, Slipher had gathered spectra of 25 spiral nebulae, and 21 of them were redshifted. They were running away from us, at speeds of hundreds and sometimes 1,000 kilometers per second. By 1923, his tally had grown, and the pattern had grown with it. Of 41 spiral nebulae, 36 showed the same red-shifted retreat. Whatever these strange world objects were, they were, almost every one of them, receding. Slipher himself, characteristically, did not draw the largest conclusion. He simply reported his data cleanly and carefully. He would live a long life. He would die in Flagstaff in 1969, 3 days short of his 94th birthday, having watched the field he had quietly seeded grow into a discipline he could scarcely have imagined. But the largest conclusion, the one that reshaped every idea we had about the universe, was drawn by others. The first of them was a Belgian priest with a doctorate in physics. His name was Georges Lemaitre, and he was, by all accounts, a warm and slightly rumpled man, deeply Catholic and deeply mathematical, unbothered by the supposed tension between the two. Lemaitre had studied at Cambridge, then at Harvard, and he had received his doctorate from the Massachusetts Institute of Technology in 1926. He was intimately familiar with Einstein's theory of general relativity, which had been published a decade earlier and which, in principle, described the behavior of space and time and matter across the entire universe. Einstein himself had already applied his equations to the cosmos, and to keep the resulting universe from either collapsing under its own gravity or flying apart, he had inserted an extra term, a fudge, essentially, that held things comfortably still. A Dutch astronomer named Willem de Sitter had produced a different solution in which the universe was empty and expanding. Neither was fully satisfying. One had matter but no motion. The other had motion but no matter. Lemaitre, working quietly, found a third way. In 1927 he published, in the Annales de la Société Scientifique de Bruxelles, a paper whose title, in translation, reads roughly as "A homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of extragalactic nebulae." It was not a modest title. It contained, within its precise clauses, the whole of the idea. Space itself, Lemaitre argued, was expanding. Galaxies were not moving through space so much as being carried along with it, as a piece of cork is carried on the surface of a slowly swelling tide. The redshifts Slipher had been so patiently collecting were not the sign of galaxies fleeing outward from some central explosion into a static void. They were the sign of the very stage on which galaxies stood, stretching. And if space was expanding, then it must once have been smaller and once, long ago, it must have been very small indeed. Lemaitre followed the logic to its source and imagined the universe as it might have looked in its first moment, and called it, in a phrase that has survived in astronomy ever since, the primeval atom. His paper, published in French in a small Belgian journal, was little read at first. He sent a copy to Einstein, who is said to have replied, with a courtesy that concealed a fair amount of scepticism, that the mathematics was correct but the physics was abominable. Einstein at that moment still believed in a static universe. He would not believe it for much longer. The observational proof came 2 years later from a mountain in Southern California called Mount Wilson. On its summit sat what was then the largest telescope in the world, a 100-inch reflector, the Hooker, whose great mirror had been ground and polished by hand, and which could gather light from objects vastly fainter than anything the smaller instruments could reach. The astronomer at its eyepiece was an American named Edwin Hubble, born in 1889, a former college athlete, a former lawyer, a former soldier, a man with a broad face and a pipe and an accent he had acquired, unnecessarily and permanently, during a brief stay in England. Hubble had already, in the mid-1920s, done something remarkable. On a photographic plate taken on the 4th of October 1923, he had identified, inside the Andromeda spiral, a single star of a particular kind, a Cepheid variable, whose brightness pulsed regularly, with a period of about 31.5 days. This was the key that unlocked the distances. Cepheid variables were understood to obey a strict rule. The longer their pulse, the more luminous they truly were. Measure the pulse. You knew the true brightness. Compare the true brightness to the brightness you saw, you knew the distance. Hubble's Cepheid in Andromeda was, by his calculations, roughly 7,000 times more luminous than the Sun, and yet it appeared as only the faintest of dots, which meant Andromeda was not a cloud of gas inside our own galaxy at all. It was an entirely separate island of stars unthinkably far away. Overnight, the universe grew from a single galaxy into a universe of galaxies. Hubble kept going. He measured Cepheids in more spirals, he calculated their distances, and then, using Slipher's redshift measurements, which he took, gratefully and without much acknowledgement, from the older astronomer's careful work, he plotted distance against velocity. The result, when he saw it in 1929, was a clean and simple line. The farther a galaxy was, the faster it was moving away. Not just moving away in exact proportion to its distance. Double the distance, double the recession speed. This was Lemaitre's expanding universe, drawn as a graph. Einstein visited Mount Wilson not long afterward. He conceded the point. The static universe was gone. The cosmological constant he had inserted into his equations to keep things still, the fudge, he would later reportedly call his greatest blunder. We will come back to that phrase in a while, because it turned out to be more complicated than he knew. There is a simple image that people have been using ever since to describe what Lemaitre and Hubble had found, and it is worth pausing on it here, because it is genuinely useful, and because it is genuinely misleading in exactly the right ways. Imagine a loaf of raisin bread, uncooked, sitting in a warm oven. The dough is full of raisins scattered more or less evenly through it. As the dough bakes, it rises, it swells in every direction. And as it swells, every raisin finds itself moving away from every other raisin. Not because the raisins themselves are motoring around in the dough, they are not moving through the dough at all, but because the dough between them is expanding. If you were a raisin with a small telescope, you would look out at your neighbours and see them receding. You would see the nearby raisins receding slowly, and the more distant raisins receding faster, because there is more dough between you and them to expand. Every raisin in every part of the loaf sees the same thing. There is no centre, there is no edge, there is only expansion, everywhere at once. Galaxies in this picture are the raisins, space is the dough, and the redshift of a galaxy's light is not the pitch shift of a passing train. It is the gentle stretching of the light waves themselves as they cross the swelling dough on their way to us. The image is not perfect. Real space, unlike a loaf of bread, does not have an outside or an oven, but it captures the essential thing. The universe is not a static container within which galaxies drift. The universe is what expands. And now we can begin to say precisely what the astronomer on Mauna Kea is seeing and what she is not. The photons arriving at her sensor tonight from Able 2029 set out from a place that was, at the moment of their departure, closer to us than the cluster is now. The photons crossed DOE that was, at every moment, expanding. Their wavelengths were stretched gently and continuously along the way. When they finally arrived, they arrived reddened, exactly as Slipher's plates showed 100 years ago, and the cluster itself, meanwhile, has kept receding. It is farther from us now than it was when the light left, and it will be farther from us tomorrow than it is tonight. If the recession followed a simple rule, if galaxies at a given distance receded at a given speed, forever and always, then the picture, though strange, would still feel manageable. There would be nothing final about it. But the rule, as Lemaitre's mathematics allowed, and as the 20th century would slowly discover, is quantitative in a way that leads somewhere very startling. It leads to a place where the recession speed, at a great enough distance, meets the speed of light. The number that governs the rule is called the Hubble constant. It is the slope of the line Hubble drew in 1929, the ratio of how fast a galaxy recedes to how far away it is. Its modern value is a matter of some spirited disagreement. Measurements from nearby distance ladders give around 73 kilometers per second per megaparsec, while measurements from the cosmic microwave background give around 67, and the gap between them is stubborn enough that cosmologists have given it a name, the Hubble tension. But for tonight the useful figure is roughly 70 kilometers per second per megaparsec of distance. A megaparsec is about 3.25 million light years, so a galaxy 1 megaparsec away is receding from us at 70 kilometers a second. A galaxy 10 megaparsecs away is receding at 700. A galaxy 100 megaparsecs away is receding at 7,000. The line keeps going, and at a distance of roughly 4,300 megaparsecs, a little over 14 billion light years, the line reaches the speed of light itself. A galaxy at that distance, by the Hubble constant we measure today, is receding from us at 300,000 kilometers a second. Beyond that distance, galaxies recede from us faster than light. There is a name for the boundary at which this happens. It is called the Hubble sphere. The first time you encounter this fact, it sounds like a violation of everything you were told as a schoolchild. Nothing, we were told, can travel faster than light. Einstein said so. Einstein was right, and yet here are galaxies, apparently outrunning the very photons they emit. How can this be legal? The answer is that nothing, in fact, is travelling faster than light. Nothing, in the sense that Einstein meant, is travelling at all. The galaxies at the Hubble sphere are not motoring away from us through space at superluminal speeds. They are, as far as their own local physics is concerned, sitting more or less still, drifting slowly with respect to the matter in their immediate neighbourhoods, exactly the way our own Milky Way is drifting slowly with respect to ours. What is happening is that the space between us and them is expanding, and there is no rule in general relativity that limits how fast space can stretch. Einstein's rule applies to motion through space. It does not apply to the stretching of space itself. This is a distinction physicists sometimes describe with a small shrug and a phrase that captures it neatly: faster than light and legal. Nothing in the equations forbids it. Nothing in 100 years of observation contradicts it. It is simply how the universe is made. And it means that some galaxies, the ones beyond a certain distance, the ones whose recession is now, tonight, superluminal, are in a peculiar position with respect to us. Their light, or some of their light, has already reached us, having set out when the cluster was closer and the intervening space smaller. That is why we can still see them. Their old letters are still arriving. But any signal we sent to them tonight, a radio pulse from the largest transmitter on Earth, a beam of laser light aimed carefully into the eyepiece and turned outward, would find itself trying to cross space that was expanding faster than the signal could travel. It would fall behind. It would never arrive. Not in a million years, not in a billion, not ever. That is a strange thing to sit with. It is, in a way, the strangest thing in this whole documentary. We are used to distance as an obstacle that time can, in principle, overcome. Given enough centuries, a message reaches its destination. That has been the shape of our imagining since we first learned to send messages at all. But there are places in the sky, tonight, that lie past a boundary in the geometry of space itself, past which no message sent from this mountain, at this hour, could ever reach them. The boundary is not a wall, it is not a place, it is a condition of space-time. And it is what physicists mean when they use the phrase we will need for the rest of this night. A cosmological horizon. The Hubble sphere is one such horizon, though as we'll see it is not quite the sharpest one. There is another subtler boundary farther out that draws the true edge of what we can ever send a signal to. That boundary sits, in the best current models, at around 17 billion light years, and it is the one that seals the letters. Everything within it is, in principle, still reachable. Everything beyond it is not and never will be, no matter how patient we are, no matter how long our species endures, no matter how clever our engineering becomes. And here is the fact that turns this from an abstract exercise into a quiet, personal one. Of the galaxies whose light is arriving at Mauna Kea tonight, the galaxies we can still see, the galaxies whose portraits fill our atlases and our textbooks and our dreams, only about 6 in every 100 are still on our side of that 17 billion light-year line. The other 94 are already beyond it. Their old letters are still arriving, their new addresses are unreachable. And every year, by the best estimates, about 160 billion more stars, spread across the countless galaxies at the fading edge, cross the line and join the unreachable 94. The astronomer in her dome does not feel any of this happening. The mountain is quiet. The dome turns. The sensor counts photons, one by one, from a place a little over 1 billion light years away, whose light set out before there were creatures on Earth with eyes complicated enough to notice it. Nothing on Mauna Kea tonight tells her that a certain small number of galaxies, somewhere far out in the field of view, are at this moment slipping across a boundary in space-time and becoming, quietly and permanently, places we can never write to again. But it is happening. It has been happening for as long as there has been an it. And to understand why the boundary exists at all, and why it is closing, and what has been quietly accelerating out there in the dark to make it close, we have to turn next to a small mathematical term that Einstein once inserted into his equations, then took out again in embarrassment, and then, 70 years after his death, found to have been right about all along. The story of that term begins, as so many stories in modern physics do, with a man at a desk in Berlin trying to make a set of equations behave. The year was 1917. The war was still on. Einstein had, less than 2 years earlier, completed the general theory of relativity, and he was now turning its machinery on the largest possible subject, the shape of the universe itself. The equations he had written were beautiful and strict. They said that matter tells space how to curve and curved space tells matter how to move, and when he applied them to the cosmos as a whole, treating the universe as a single enormous problem in geometry, the equations told him something he did not want to hear. They told him that a universe filled with matter could not sit still. It had to be doing something. It had to be either expanding or contracting, pulled inward by its own weight or pushed outward by some other cause. It could not simply be. To Einstein, and to almost every physicist and astronomer of that generation, a universe that could not simply be was not a universe at all. The stars had always been there. The stars would always be there. The sky was, by every philosophical and scientific instinct of the age, an eternal and unchanging thing, with local motions and slow ancient drifts, but no overall career. A cosmos with a beginning or an end belonged to theology, not to physics. And so Einstein, and faced with equations that insisted on motion, did what a careful theorist does when the mathematics disagrees with the world. He added a term. The term was a single Greek letter, a capital lambda standing for a constant. It represented a kind of uniform pressure built into the fabric of space itself, a small outward push present in every cubic centimetre of vacuum, exactly balancing the inward pull of gravity on the larger scales. With lambda set at just the right value, the equations relaxed. The universe could sit still. The stars could remain where they were. The cosmological constant, as he called it, was a small mathematical courtesy paid to the intuitions of an entire civilization. It held for barely a decade. The rest of the story we've already touched on. Slifer at Flagstaff, patiently tearing the light of the spiral nebulae into its component colours and finding that almost all of them were sliding toward the red. Lemaitre, the Belgian priest, deriving in 1927 the mathematics of an expanding cosmos and proposing that everything had begun from a single primeval atom. Hubble at Mount Wilson, with the great 100-inch mirror and the Cepheids, and the velocity distance law of 1929 that finally made the expansion undeniable. What we have not yet dwelt on is what all of this did to Einstein, because when he travelled to Pasadena in the early 1930s and stood with Hubble at the eyepiece and saw for himself the evidence that the universe was not in fact sitting still, that the whole grand assumption on which his cosmological constant had been built was simply wrong, he abandoned the term. He wrote it out of the equations. He said, in the years that followed, that its introduction had been the greatest mistake of his professional life. The story that he called it his greatest blunder comes to us through the physicist George Gamow, who reported the phrase in his memoirs, and historians have argued ever since about whether Einstein used exactly those words or something quieter and more rueful in his letters. What is not in dispute is the feeling. He had bent his beautiful equations to preserve a picture of the cosmos that turned out not to be true. He had missed, by inserting a fudge, the chance to predict the expansion himself years before Hubble's photographs made it undeniable. The lambda was banished. The equations were allowed to say what they had always been trying to say. And for most of the 20th century, the cosmological constant slept in the footnotes of textbooks, a curiosity mentioned mainly as a cautionary tale about what happens when a great physicist tries too hard to be reasonable. That is where the term stayed, more or less untouched, for 70 years. And that is the state of the field, roughly, into which two rival teams of astronomers walked in the middle of the 1990s holding a very different question in their hands. The question was not whether the universe was expanding. That had been settled since Hubble. The question was how the expansion was changing over time. Every galaxy in the sky pulls on every other galaxy through gravity, and gravity, patient and undiscriminating as it is, should be slowing the whole outward rush down. The universe was thought to be like a ball thrown upward from the surface of a planet, still rising certainly, but decelerating as it went, its climb gradually softened by the weight of everything inside it. The only real question was by how much. Would the expansion slow gently and continue outward forever, thinning into a cold, quiet future? Would it slow enough to halt and then reverse, drawing the galaxies back together into a mirror image of the beginning? To answer that question, you needed a way to measure how fast the universe had been expanding in the distant past, and to compare it against how fast it was expanding now. You needed, in other words, a ruler and a stopwatch that could reach across billions of years. The ruler the two teams chose was a particular kind of stellar death. A type Ia supernova is what happens when a white dwarf, the small, dense, cooling remnant of a sun-like star, accumulates too much matter and passes a certain critical threshold. Beyond that threshold, a runaway thermonuclear detonation tears the star apart in a burst of light so bright that, for a few weeks, a single type Ia can outshine an entire galaxy of 100 billion suns. And because the threshold is a matter of fundamental physics, a fixed mass at which the dwarf can no longer hold itself together, Every type Y in the universe detonates at more or less the same intrinsic brightness. They are, to use the astronomers' cherished phrase, standard candles. Standardizable ones, more precisely. Small corrections have to be applied for the shape of the light curve, the pace at which each supernova brightens and fades. But the principle is the same. If you know how bright the candle truly is, and you measure how bright it appears, you can work out how far away it is. And if the same candle also carries a redshift, telling you how much the universe has expanded during the journey of its light, then you have, in a single object, both a distance and a stretch. You have the ruler and the stopwatch together. The first team, the Supernova Cosmology Project, had been at this the longest. It had been co-founded in 1988 at Lawrence Berkeley National Laboratory by a young physicist named Saul Perlmutter, who would spend the next decade building up the techniques for finding these fleeting explosions on demand, scheduling telescope time in advance, comparing images of the same patch of sky taken weeks apart, catching new points of light before the moon rose and washed them out. Supernova hunting had once been a matter of patient luck, waiting for a bright new star to appear and hoping someone had a telescope pointed at the right piece of sky. Perlmutter's team, and the software they wrote, turned it into something closer to an industrial process, a machine for producing standard candles at cosmological distances on a predictable schedule. The second team formed later, and partly in response. In 1994, a young astronomer named Brian Schmidt, freshly finished with his doctorate at Harvard the year before, gathered a rival collaboration together and gave it the plain, descriptive name of the High Z Supernova Search Team, the Z standing for redshift, the higher the better. The methods were similar to those Perlmutter's group had pioneered. The distances would be greater, the ambitions were the same. Schmidt led the collaboration. The analysis of the team's data would be led by another young astronomer, Adam Rees, born in Washington in 1969, who had earned his own doctorate at Harvard in 1996 and was, by the time the results began to arrive, still in his 20s. Two teams then, two independent efforts. Two sets of telescopes turning to the same class of distant explosion, hoping to measure the same slowdown, working in the way of good rival science, with a wary and watchful respect for each other's progress. And both of them, in the last months of 1997 and the first months of 1998, began to find the same wrong thing. The distant supernovae were too faint, not by an enormous margin, not by anything a single measurement could have established, but consistently across candle after candle in both teams' data. A type year at a given redshift ought to have appeared at a certain brightness, according to the standard picture of a decelerating universe. The ones the teams were seeing appeared dimmer than that. They were further away than they should have been. The light that had left them, back when the universe was younger, had been travelling through a cosmos that had, in the intervening billions of years, expanded more than a decelerating model allowed. There was only one way the equations could produce that pattern. The expansion had not been slowing down. It had been, and still was, speeding up. It is difficult to convey how unwelcome this result was at first, even to the people finding it. Both teams spent months looking for the mistake. They checked the dust that might be dimming the light along its long journey. They checked the possibility that ancient supernovae might be intrinsically slightly different from nearby ones. They checked their photometry and their calibrations, and the small corrections applied to the shapes of the light curves. Nothing they checked would go away. In January of 1998, Perlmutter announced the Supernova Cosmology Project's surprising result at a scientific meeting. The expansion of the universe was not slowing down. The High Z team, working through their own data, reached the same conclusion within weeks. The first results from the High Z team, based on 10 supernovae, were published in the Astronomical Journal later that year. The Supernova Cosmology Project's results, based on 42, appeared in the Astrophysical Journal in 1999. Between them, the two teams had studied more than 50 distant Type Ia supernovae, and every one of them told the same story, softly, From the far side of billions of years, the candles were too dim. The universe had been carrying them away faster than gravity alone would allow. The journal Science at the end of the year named the accelerating universe its breakthrough of 1998. The award was joint, given to both collaborations at once because there was no way to disentangle them, and no scientific reason to try. It was the kind of coincidence in which two independent teams, with different personnel and different telescopes and different analysis pipelines, arrive at the same impossible answer at almost the same moment, and by doing so save each other from the natural suspicion that one of them has made a mistake. 13 years later, in 2011, the Royal Swedish Academy of Sciences would award the Nobel Prize in Physics to the three men most closely associated with the finding: Saul Perlmutter, Brian Schmidt and Adam Rees, with one half of the prize going to Perlmutter and the other half divided between Schmidt and Rees. Along with the diploma and the gold medal came a purse of 10 million Swedish krona, a little over $1.5 million United States dollars at the time, split by the same formula. But the true recognition had come already in the quiet months of 1998, when the two rival teams looked at each other's data across the walls between them and understood, slowly, that they were both right. And that meant something in the equations had to give. The universe was accelerating. Ordinary matter, the stars, the gas, the dust, the dark matter that outweighs them all, could not do that. Gravity, in every form we understood, pulled things together. What was needed was something that pushed them apart uniformly everywhere on the larger scales, gently but relentlessly over billions of years. Something that had been quietly at work in the equations of general relativity all along, waiting for the moment when the world would need it again. Something with a Greek letter already reserved for it, in a footnote of a textbook, next to a cautionary anecdote about a great physicist's mistake. Einstein's cosmological constant was quietly and without fanfare exhumed. It came back changed. It was no longer a small courtesy paid to a static universe. It was now a positive quantity, a genuine outward pressure of space itself, small enough to have been irrelevant in the young dense cosmos, but large enough, once the matter had thinned out sufficiently over billions of years of expansion to take over the equation. In the modern language it acquired a new name, one that made no pretense of understanding what it was: dark energy. The word dark in astronomy is a confession dressed as a description. It means that whatever this thing is, it does not shine, does not absorb, does not interact with light in any of the ways that would let us see it directly. It shows up only in its gravitational effect on the cosmos as a whole, and even there its effect is the opposite of what gravity is supposed to do. It repels, it pushes, it stretches. And in the current picture, drawn from the most careful measurements of the cosmic microwave background and the distribution of galaxies and, yes, the continuing survey of Type Ia supernovae, this dark energy makes up somewhere close to 68% of the total energy content of the universe. Dark matter accounts for another 27%. Ordinary matter, the substance of the stars and the planets and the astronomer and the mountain she stands on, everything ever seen, ever touched, ever named, comes in at around 5%. 5%. That is the fraction of the universe made of the kind of stuff that interacts with light, the kind of stuff that can, in principle, become a person on a mountain looking through a telescope. The other 95 is composed of two ingredients whose names admit, honestly, that we do not know what they are. And of those two, the larger by far is the one now driving the acceleration. The engine of the whole closing sky is a term in any equation. It has a value. It has an effect measurable to several decimal places. It does not have at present an explanation. Physicists have proposals, the vacuum energy of quantum fields, subtle features of the geometry of space-time, whole families of ideas gathered under the name quintessence, and none of them, at the moment, sits comfortably in the equations at the value the sky is measuring. Einstein's constant is back, and it works, and no one alive knows why. It is worth pausing on the emotional shape of that fact for a moment, because it matters to everything that follows. In the ordinary story of science, a mystery is a temporary condition, a placeholder for the answer that a later generation will find. The blank on the map fills in eventually, and it is possible that dark energy will follow that pattern, that a physicist not yet born will one day give a satisfactory account of what the vacuum is doing, and Lambda will lose its air of embarrassment for the second time in its life. But for now, and for the entire span of this documentary, and for the sky at Mauna Kea tonight, dark energy is a named thing that is not an understood thing. It is the shape of a gap in our knowledge, given a symbol so that we can put it into the equation and get the right answer. And the right answer, when you put it in, is this. The expansion is speeding up. It has been speeding up for something like the last 6 billion years, since the universe grew thin enough for the constant term in the equation to overtake the gravitational term. It will continue to speed up. And as it does, the horizon we spoke of earlier, the 17 billion light-year line, the boundary past which no signal we send tonight can ever arrive, draws inward, quietly, all the time. That is the deep sadness woven into the accelerating universe, and it is the sadness we are going to sit with for the rest of the night. When Einstein first added his lambda, he did so to keep the sky still. When Hubble showed him that the sky was not still, he took it out again. What no one guessed in 1917 or 1929 or 1931 was that a version of the term he had introduced and abandoned was actually there, at a small positive value, doing precisely the opposite of what he had originally used it for. It was not holding the cosmos steady, it was pushing it apart. And the pushing, over the immense timescales that cosmology reckons in, was destined to change everything about what the universe would look like from any observer's window, including the small dark window on top of a mountain in Hawaii, and the small human window of a species that had only very recently learned to look out. If lambda was 0, the sky would still be a story of loss, but it would be a slower one. A merely coasting universe, expanding on the inertia of the Big Bang but neither speeding up nor slowing down, would carry galaxies away from us, but its horizon would open outward as time passed. Given enough patience, given enough centuries, we would eventually see more of the cosmos, not less. New light, from farther and farther away, would keep arriving. The record would grow, the atlas would thicken. Nothing would ever slip permanently out of reach in the way that things are slipping now. But lambda is not 0. Lambda is a small positive number, buried in the equation, and its consequence is that our horizon does not open. It closes. The volume of the universe from which we could ever, in principle, receive a fresh signal is shrinking. The volume to which we could ever, in principle, send one is shrinking too. And every galaxy, currently more than about 18 billion light-years away, in the units that cosmologists use for the present-day distance to distant objects, is already on the far side of that shrinking boundary, receding through space that is expanding faster than any signal we could send could ever cross. No matter how much time passes, no matter what our descendants build, no matter how patient a civilization could ever be, the astronomer on Mauna Kea watching Abell 2029 climb the sky does not need to think about any of this in order to do her work. The photons arrive, the camera counts them, the calibration frames come and go. The cluster she's imaging tonight, at a little over 1 billion light-years, is safely inside the horizon. Its light will keep arriving, and any hypothetical message we sent toward it would, in the models, eventually get there. But somewhere in her wider field of view, in the faint smear of much more distant galaxies at the edge of the frame, there are objects near the line. Some of them, over the course of tonight's exposure, have moved through it. Their old light, the light already in flight, the light that set out toward this mountain 1 billion or 2 or 5 billion years ago, will keep coming, faithfully, for as long as this instrument exists to catch it. But nothing we send back tonight will reach them. Nothing we send tomorrow will reach them. Nothing we send in 1,000 years, from a telescope not yet imagined, will reach them either. The sky over her dome is, in the most literal sense, a record of things we can see but can never touch. And the record is right now, quietly closing. That is the fact the rest of this documentary lives inside. It is a fact so strange and so gentle in its strangeness that it takes a long time to feel. There are two different edges to speak of in the geometry of the closing sky, the edge of what we can see and the edge of what we can reach. And they are not the same edge, and the difference between them is where the whole heartbreak of the story sits. But before we can walk carefully around those two edges and understand why the number 94 keeps coming back to us, we should sit for a moment longer with what has just been said. A term Einstein put into his equations to keep the universe still turns out, a century later, to be the very thing making it run away from us. His greatest blunder was not a blunder. It was a whisper of the real answer, guessed for the wrong reason, and dismissed for the right one, and rediscovered by two rival teams of astronomers hunting for the deaths of distant stars. And the answer, once heard, cannot be unheard. The universe is accelerating, the horizon is closing, and the sky, patient and beautiful and full of light, is a room whose doors, one by one, are quietly being shut from the outside. It is worth pausing on the fact that there are two edges, and not one, at the boundary of everything we can know. The instinct is to imagine a single wall around the universe, a sphere with the Earth at its centre, the stars painted on its inner surface, and beyond it, nothing that concerns us. That is the picture most of us carry from childhood, and it is close enough to the truth for most purposes, and it is wrong in exactly the way that matters here. There is not one wall, there are two. They sit at different distances, they mean different things, and the gap between them, quiet and unmarked and easy to miss, is where the strangeness of our situation lives. The outer wall is the one most people have heard of, though usually by a name that hides what it is. It is called the observable universe, or, in the more technical language, the particle horizon. It is the boundary drawn by the age of the cosmos itself. Light travels at a fixed speed. The universe has been in existence for a finite time, and so there is a sphere around us, vast but finite, inside which light has had enough time, since the beginning, to reach the Earth. Everything whose ancient photons have arrived, or could still be arriving, sits inside that sphere. Everything whose light has not yet had time to cross the distance sits outside it. That is the outer wall. That is the limit of the scene. In the units cosmologists use for present-day distances, the comoving distances, which strip out the effects of expansion and describe how far apart two objects are right now, tonight, as we are speaking. That outer wall sits at roughly 46 billion light-years from the Earth. Not 13.8, though the universe is only 13.8 billion years old. 46. The number seems, at first hearing, to be a mistake. How can we see anything that is farther away, measured in light-years, than the age of the cosmos in years? Nothing travels faster than light. The photons arriving in the telescope tonight have been in flight for at most 13.8 billion years, and yet the object that emitted them, calculated forward to where it sits now, has been carried by the expansion of space to a distance more than 3 times, greater than the flight time of its own light. That is what expansion does. It stretches the road while the traveller is on it. The photon that left a young galaxy near the beginning of everything set out toward what would become the Milky Way, when the distance between them was small. As it travelled, the space it was travelling through swelled outward, and by the time it arrived on this mountain tonight, its point of origin had been carried far beyond it. The light is old. The source of the light now is somewhere else entirely, much farther away, and often still receding. The observable universe is not a snapshot of where things are. It is a slow accumulation of arrivals from where things were, projected outward, in the mind of the cosmologist to where those things must be now if the models are right. 46 billion light years. That is the outer wall. That is the edge of what we can see. And then, sitting quietly inside that outer wall, there is a second boundary, closer in, much less discussed, and in some ways much more consequential. It is called the cosmic event horizon. It is not the edge of the seen, it is the edge of the reachable, and it sits in the present-day distances at roughly 16 billion light-years from the Earth, a little more than a third of the way out to the particle horizon and no farther. The distinction is worth turning over slowly because the whole shape of what follows depends on it. The particle horizon at 46 billion light-years is the boundary drawn by the past. It answers the question, from how far away has light already had time to reach us? The event horizon at 16 billion light-years is the boundary drawn by the future. It answers a different question, and a harder one. From how far away could a signal sent by us tonight ever hope to reach any destination beyond, at any moment for the rest of time? The first horizon is about arrival, the second is about departure. And in a universe that was merely coasting outward, expanding but not accelerating, the two would converge, given enough time, and every point within the observable would eventually also be reachable. The particle horizon would keep opening. The event horizon would open with it. Nothing would be lost. But we do not live in that universe. We live in a universe with lambda in the equations, and lambda means acceleration. And acceleration means that the two horizons come apart and stay apart. The outer wall keeps growing, slowly, as ancient light continues to arrive from farther and farther back. The inner wall, the horizon of reachability, is closing, and the space between them, the great volume of the visible from which nothing can now be reached and to which nothing can now be sent, is expanding night after night with every rotation of the sky. Set the great distances aside for a moment and think instead about what the second horizon actually is, in the plainest possible terms. Imagine sending a photon, right now, from the top of Mauna Kea, aimed at a chosen galaxy in the deep field. The photon leaves the mirror. It travels through the atmosphere, out past the moon, past the outer planets, past the heliopause, out into the intergalactic dark, at 300,000 kilometers a second, the fastest anything is permitted to move. It carries no message worth reading, but it carries the principle. This is the fastest possible reach we have. If that photon, given all the time between now and the end of the universe, could arrive at the chosen galaxy, then that galaxy is inside the event horizon. It is reachable, if, no matter how patient we were, no matter how long we waited, that photon would never close the gap, because the space between us and the target is expanding faster than the photon can cross it, and expanding faster still with every passing giga-year. Then the galaxy is outside the event horizon. It is unreachable forever. Not because we lack the technology, not because the distance is very great, because the geometry of the universe forbids it. 16 billion light-years. That is where the line sits tonight. Every galaxy whose present-day distance from us is greater than that number, and the vast majority of galaxies in the observable universe are farther than that, is already on the far side of the fence. We can see them. Their old light, released long before the fence was where it is now, is still in flight, still arriving, still being counted by the calibration frames on quiet mountains. But nothing new we do can ever touch them. No spacecraft, no signal, no message written into the atmosphere of the Earth, no civilization, no prayer. The photons that left them 1 billion years ago are honouring their old promise. The photons we send tonight are travelling toward a destination that is receding in the frame of the space between us faster than they can chase. There is a kind of quiet arithmetic to this that resists intuition for as long as one holds it in the head and only settles when one lets the numbers become an image. Picture the map of everything we can see, spread out on a table. 46 billion light-years, edge to edge across the radius. A sphere. Inside it, hundreds of billions of galaxies arranged in filaments and walls and clusters, and the vast, nearly empty voids between them, the whole cosmic web with all its knots and threads. Now, on that map, draw a smaller sphere, centred on the Earth, with a radius a little more than a third of the way to the edge. The smaller sphere is the region from which anything we do tonight could ever, in any future, reach. Everything outside the smaller sphere and inside the larger, the shell of severed connection, the great annulus of the seen but unreachable, is the country the rest of this story is set in. The ratio of those two volumes is the source of the number that opened the whole documentary. When one takes the sphere of the observable and subtracts the sphere of the reachable, the volume that remains, the volume of galaxies we can see but never touch, is around 94% of the total. Every 100 galaxies in the deep field images, roughly 6 lie within the shrinking bubble of reachability, and roughly 94 lie outside it. The overwhelming majority of the visible universe is already, tonight, sealed off, not fading, not receding into difficulty, already past the fence. The line has moved through them, and they have not noticed, and neither have we, because from the inside of the geometry nothing looks any different than it did a night ago. It's easy to forget how strange it is that the sky can be a record of severance, while also being a record of light. The two facts sit together and do not contradict each other. The photons arriving on the mirror tonight are real. The galaxies they came from are real. The image the camera builds up over the course of an exposure is honest. It is not a memory of a lost country or a picture of ghosts. Those galaxies exist. They're shining now, more or less as they were, evolving quietly under their own gravity, forming stars, cooling, growing old. The severance is not a severance of existence. It is a severance of causal connection, a severance of the possibility that anything we do could ever influence them, or anything they do from this moment on could ever influence us. The light that left them long ago is still in the mail. Nothing new will be posted in either direction ever again. Turn the story for a moment so that the light falls on one of the most famous images ever taken by any human instrument. In December of 1995, the Hubble Space Telescope was aimed at a small, nearly empty patch of sky in the constellation Ursa Major, high in the northern sky, above the handle of the Big Dipper. The patch was chosen because there was, so far as the surveys knew, nothing much in it. No bright stars, no nearby galaxies, no clusters, no interfering foreground. It was a keyhole into the deep field. For 10 days, from the 18th to the 28th of December, the telescope stared at that keyhole and gathered its faint arrivals, one photon at a time. The result, released the following month, was the Hubble Deep Field. It showed roughly 3,000 galaxies in a patch of sky about the angular size of a tennis ball held 100 meters away. Almost a decade later, from September of 2003 into January of 2004, the successor image was assembled from something like 800 separate exposures aimed at another quiet patch, this time in the southern constellation Fornax. The resulting picture, the Hubble Ultra Deep Field, contained nearly 10,000 galaxies in a field of view a little larger than 3 arc minutes on a side, a portion of the sky small enough that the whole sky, tiled with such fields, would take some 26 million of them to cover. 10,000 galaxies in a grain of sand held at arm's length, and behind that grain of sand another grain, and behind that another, until the mind mercifully stops trying to imagine it and simply accepts the total. The deep field images are among the most quietly moving photographs in the history of our species, because they are photographs of nothing much, taken carefully enough that nothing much turned out to be everything. Every faint smudge is a city of stars. Every tiny arc is a system that has been shining for billions of years. Every colour, the reddened, stretched light of the more distant ones, the bluer light of the nearer, is a signature of both distance and time. It is a family photograph in which almost every relative is a stranger, and almost every stranger is a stranger we will never meet. And here is the fact that presses down softly on those images once the geometry is understood. Of the 3,000 galaxies in the Hubble Deep Field, and the 10,000 in the Ultra Deep Field, the overwhelming majority sit at distances well beyond the 16 billion light-year event horizon. The great crowd of them are on the far side of the fence. They are visible because their old light has already made the crossing. They are unreachable because any new light we send has no hope of ever making it across in the other direction. What looks in those images like a crowd of possible destinations is very nearly a crowd of severed addresses, a postal directory printed after the roads have already been washed out. Beautiful, comprehensive, useless as a map of anywhere we could go or of anywhere from which anyone could ever come to us. There is a detail here that is easy to pass over, and it deserves to be sat with. The deep field images are used quite rightly to teach children how vast the universe is, how many galaxies it contains, how humble our place in it is. The lesson is delivered with a kind of wonder that belongs to the daylight side of the story. But the same images, seen through the geometry of the event horizon, deliver a second lesson, quieter, that belongs to the night. They are not only a portrait of abundance, they are a portrait of loss already accomplished before anyone alive today was born, before the telescope was even conceived, before the mountain it now flies above had cooled from its last eruption. Almost every one of those tiny lights lies on the far side of a boundary that closed on it, long before we noticed there was a boundary at all. There is a smaller, quieter story woven through all of this, and it belongs to the great structures nearer to home. Consider the Perseus-Pisces supercluster, one of the most massive coherent structures in the local universe, a filament of thousands of galaxies bound loosely together by gravity, spanning something on the order of 300 million light-years and lying at a distance of roughly 250 million light-years from us. In the geometry of the closing sky, Perseus-Pisces is close. It is intimate. It is a neighbour. It sits well within the reachable sphere, in the small 6%, and its galaxies are companions of a kind, bound to the same great web of matter that includes our own local group, drifting through the same stretched space, illuminated by the same aged light. Beyond it, at greater distances, the superclusters and filaments become steadily more foreign. Some are still within the sphere of reach. Many are not. And out at the far edges of the deep field, in the delicate faint tracery that the Hubble images resolve as tiny reddish smudges, whole populations of galaxies sit at distances where the geometry has already spoken. They are visible, they are not reachable. The line has passed through them. It is worth trying just once to feel the shape of that. Not to calculate it, not to model it, simply to feel it. If a signal were sent tonight from every observatory on Earth, aimed at every galaxy in the ultra-deep field, with the intention that some future civilization in some unimaginable epoch might one day pick up any one of those signals and know that we were here, the honest answer is that fewer than one signal in 15 would ever arrive at its destination. The rest would travel outward forever, chasing recessions they cannot catch, weakening in a space that keeps stretching underneath them until the photons themselves became too thin and too red for any instrument to detect. Not lost to distance, lost to geometry, lost to the small positive number in the equation that Einstein once put in and then took out, and that the universe, in its own patient way, put back. There is the matter too of the fence itself, and of what it means to say that it is closing. It is tempting to picture the event horizon as a wall standing at a fixed distance, a marker that has always been at 16 billion light-years, and will always be at 16 billion light-years, and that galaxies sail through in a stately procession as the expansion carries them outward. But the geometry is subtler than that, and stranger. As the acceleration continues, the horizon itself, measured in the commoving distances that describe the map of the present, is actually shrinking. It is moving inward, toward us, in the frame of the underlying grid. Even galaxies that are not moving through the grid much at all, galaxies whose commoving coordinates are more or less fixed, drifting only slowly under local gravity, find the fence coming to meet them. The line does not sit still while the universe streams past. The line advances, the universe streams. Both processes work in the same direction. Both carry more galaxies across the boundary with each passing moment. Somewhere in the great voids between the filaments, in the enormous emptinesses that lie between the Perseus-Pisces filament and its far neighbours, there are faint dwarf galaxies at distances of perhaps 15 or 16 billion light-years, calm and small, doing nothing in particular, whose light has been arriving here for most of the age of the universe. As this sentence has been spoken, some of them have crossed the horizon, not with any drama, not with a change in appearance. The old light they released billions of years ago will continue to arrive for a very long time yet, slowly reddening, slowly thinning. But the future has been shut in their direction. Whatever they emit from this moment forward will never reach us. Whatever we emit toward them will never reach them. The mail has stopped, in both directions between us and each of those quiet worlds, and neither party has been informed. It is a strange kind of loss because nothing in the sky looks different. The image on the plate does not flicker. The calibration frames do not report anything anomalous. The astronomer on the mountain writes down her measurements, and the numbers behave. The severance is invisible from the inside. It is inferred entirely from the equations, from lambda in the field equations, from the distant supernova fainter than expected, from the map of two horizons that come apart under acceleration. Nothing in the light betrays that anything has happened. But when the calculation is run, when the geometry is honoured, one has to accept that the count of galaxies with which any future exchange is possible is quietly ticking downward. Tonight, every second without ceremony. The sky is not a finished record of loss. It is a record being written in real time, in ink that dries in the moment it is set down and cannot be unwritten. There's one more thing worth understanding about this, before the story moves on to what it means for the light that is still in the mail, and for the messages that will and will not arrive. The two horizons, the outer wall of the seen at 46 billion light-years, the inner wall of the reachable at 16, are not fences we invented or thresholds we drew for convenience. They are consequences. They fall out of the equations the way water falls from a tilted glass. Given lambda, given the observed expansion history, given general relativity applied to a universe on the larger scales, the two horizons must exist, and they must sit roughly where they sit, and they must behave as they do. To do the calculation is to be forced to accept the result. There is no room in the equations for negotiation, and no room in the geometry for hope of a workaround. Whatever we might one day learn about dark energy, whether it is a true cosmological constant, or something that slowly evolves, or something stranger still, the horizons close on the timescales that matter to any imaginable civilization. 6 billion years into the acceleration, the fence is where it is, and the fence is moving. And it is here, having drawn the two circles on the map, that the number 94 comes back and takes on a weight it did not have before. It is no longer only a figure quoted in the introduction. It is the ratio of two volumes on a diagram we can now picture, the small inner sphere of the reachable and the great outer sphere of the seen, and the shell between them containing almost every galaxy the telescopes have ever photographed. 94 out of every 100 on the wrong side of the fence. Losing the signal is not the same as losing the traveller, but it is worth asking gently what it means to say that 100 billion travellers are already gone, not from our sight, but from any road we might ever walk toward them, and to sit for a while with the answer. It is worth sitting for a long moment with a paper that two physicists wrote in the autumn of 2007, because it takes the question just asked and answers it with a kind of quiet mercy that only arithmetic can give. The paper was called The Return of a Static Universe and the End of Cosmology, and its authors were Lawrence Krauss, then at Case Western Reserve University in Cleveland, and Robert Scherer at Vanderbilt in Nashville. It appeared in the journal General Relativity and Gravitation in October of that year, having taken 5th prize a few months earlier in the essay competition run by the Gravity Research Foundation, a small annual contest with a long history of drawing serious minds toward questions too large for ordinary papers. It was not a long essay. It ran a handful of pages. But what it did, quietly, was to take the equations that have been threaded through this story all along and to run them forward, not by millions of years, not by billions, but by 100 billion, and to describe what a sky would look like from the inside of the answer. The calculation itself is not exotic. It uses the same field equations Einstein wrote in the winter of 1917, in the same city where he first added lambda by hand to hold the cosmos still. It uses the same measured expansion history that the two supernova teams brought back from the late 1990s, dimmer than expected, and the same value for dark energy that Planck later refined from the microwave sky. Nothing new is assumed, nothing exotic is invoked. The essay simply asks what an astronomer would see, on some clear night on some hypothetical world, 100 billion years from now, a stretch of time about 7 times longer than the universe has so far been alive, and what she could, in principle, learn from that sky. The answer, told plainly, is that she would see almost nothing. The local group, our own small parish of galaxies, of which more will be said in due course, will still be there, gravitationally bound, orbiting itself, by then merged into a single elder island of stars. Beyond it, in every direction, the sky will be dark. Not dark in the sense of a country night, with the arch of a galaxy overhead and the faint spill of neighbours behind it. Dark in the way the ocean is dark to a fish at the bottom of a trench. The other galaxies, the hundreds of billions of them that fill the plates and the deep fields tonight, will have receded so far and be receding so fast that no photon they emit will ever again cross the horizon into our instruments. The great outer neighbourhoods will have fallen off the edge of what any telescope, of any conceivable design, could gather. The cosmos will look, from her mountain, like a single island in an infinite black sea. And here is the part of the paper that catches the breath a little, once one has taken its measure. She will not know that anything is missing. She will not know that there was ever anything else. The evidence that told us, over the course of a century, that the universe is expanding, that Slipher recorded on his plates at Flagstaff, that Hubble plotted on his graph at Mount Wilson, that Perlmutter and Schmidt and Rees wrung out of their distant supernovae, will not be available to her. There will be no other galaxies whose light she can decompose into a spectrum, and therefore no redshifts to measure, and therefore no velocity distance law to notice. There will be no faint background hiss at 3 degrees above absolute zero for her to trip over in her radio telescope, because the microwave sky will by then have redshifted into wavelengths longer than her instruments, or any instruments, could reasonably reach. There will be no primordial abundance of light elements to reconcile with a hot early cosmos, because the hot early cosmos will have receded so far from any possible test that the reconciliation will be untestable. Every observational pillar on which the story we are now telling rests will, by then, have quietly walked out of the room. What she will conclude, if she's a good scientist, is that the universe is a static and eternal island, containing one great galaxy and its complement of stars, sitting in a void that has always been there and always will be. She will not be wrong to conclude this, because her data will be honest and her logic will be sound, and there will be nothing in her sky to contradict her. She will simply be looking at a smaller universe than the one that actually exists, and she will not have any way to know it. The scientific worldview she arrives at will resemble, almost eerily, the worldview that human beings held before Hubble climbed the mountain in Pasadena and pointed his telescope at Andromeda. A single luminous province, floating in absolute darkness, and no larger frame in which to place it. Krauss and Scherer note this parallel with a certain wry gentleness. Cosmology, in that future, will not be wrong. It will simply be small. It will have shrunk to fit the evidence that remained. There is a line of Krauss's, quoted often since the paper came out, in which he imagined the puzzles that future astronomers of that quiet world might set themselves. They will notice, he said, that the visible universe seems to consist of a small number of galaxies, 6, perhaps, in the version of the count he offered, and they will wonder what the significance of that number is. Hundreds of papers will be written on the question, conferences will be convened, careful theories will be proposed, and none of the papers and none of the theories will happen to arrive at the truth, which is that the number is not significant at all, and that the 6 are simply what is left after everything else has fallen over the edge. Ethan Siegel, writing about this future, has borrowed a sentence from Churchill for the occasion. "It is always wise to look ahead," he wrote, "but difficult to look further than you can see. In 100 billion years, no one will be able to see far enough to know what has been lost. The loss will have been complete, and the record of the loss will have been lost with it." The consequence of all this, when one turns the thought over slowly, is not really about that future civilization at all. It is about us. Because if the calculation is right, and there is no serious reason to think it is not given lambda and the equations and the observed acceleration, then the moment we are living in is a very unusual one. It is a moment in which the universe is still legible. The microwave sky is still glowing faintly at just under 3 degrees, hot enough for our detectors to catch, and cool enough for us to have understood what it is. The distant galaxies are still redshifting away in ways our spectra can measure. The Big Bang is still leaving fingerprints on the sky that our instruments can lift. The pillars of the cosmological story are all still standing. This will not always be true. 6 billion years into the acceleration, we are living inside the window in which the whole cosmos is still available to be read. Krauss and Scherer used a phrase for this, and the phrase has stuck. They called it a cosmological golden age. It is the epoch in which the largest questions can still, in principle, be asked and answered. It began sometime after the microwave sky cooled enough for structure to form, and it will end when the last of the distant evidence falls out of reach, and in between, for a stretch of time that is not vanishingly small on cosmological scales, the universe is transparent to itself. We are inside that stretch. The astronomer on Mauna Kea, on the mountain in the Pacific Dark, is inside it. So are the readers of the papers and the writers of them, and every telescope that has been trusted with the sky since Slipher first sat down with his spectrograph in Flagstaff. It is not that we are lucky in some sentimental sense. It is that the arithmetic of the calculation places us inescapably in the one interval of cosmic history during which a mind could work out what has happened. Before this interval, the sky was too hot and too dense to see through. After it, the sky will be too empty and too silent to notice anything at all. In between, briefly by the standards of the universe and endlessly by the standards of a life, there is a window. We are looking through it. And there is a smaller, quieter story woven through all of this, which is the story of the oldest message we have ever received, and of how it too is on its way out. Consider for a moment the noise. On a spring day in 1964 at a Bell Telephone Laboratories site in Holmdel, New Jersey, 2 radio astronomers named Arno Penzias and Robert Wilson were trying to make a very sensitive antenna quieter. The antenna itself was an unusual instrument, a horn-shaped structure of aluminium about 50 feet across, mounted on a steel base weighing many tons, built a few years earlier for satellite communications work, and now being reconditioned for radio astronomy. Penzias, then in his early 30s, and Wilson, a few years younger, wanted to point it at the sky and pick up faint sources with as clean a receiver as they could manage. To do that, they had first to account for every source of hum and hiss in the system itself. Every warm circuit contributed, every stray reflection contributed. The antenna, being open to the sky, collected a share of the ordinary radio noise of the world, and they had to subtract all of it before they could trust the residual. But there was a residual they could not subtract. A faint uniform hiss corresponding to a temperature of about 3 degrees above absolute zero was arriving from every direction they pointed the horn. It did not vary with the time of day. It did not vary with the season. It was the same when the antenna was aimed at New York City and when it was aimed at empty sky. They suspected the electronics and cleaned the electronics. They suspected the city and confirmed it was not the city. They noticed that a pair of pigeons had taken up residence inside the horn and left behind what Penzias, with the delicacy of a working scientist writing for the record, called a white dielectric material, and they cleaned that too and evicted the birds. The hiss remained. Whatever they did, the antenna kept telling them that the sky was faintly, uniformly, everywhere warm. What they had stumbled into, without at first knowing it, was the thermal glow of the universe itself in its infancy. About 380,000 years after the beginning, the cosmos had cooled enough for the free electrons and protons that filled it to settle into neutral hydrogen atoms, and in that moment the fog lifted, and light, which had been ricocheting off the charged particles like sunlight in a snowstorm, was suddenly free to travel. That first free light had been streaming through the universe ever since. It had been travelling for nearly 14 billion years by the time it reached the Holmdel Horn. Along the way, the expansion of space had stretched its wavelengths from the fierce short pulses of a young hot cosmos into the long, gentle microwaves that made the hiss on Penzias and Wilson's receiver. It was the oldest electromagnetic radiation in existence. It was, in a real sense, the earliest photograph the universe had ever taken of itself, and every direction of the sky was in the frame. The discovery, once its meaning was understood, changed cosmology decisively. It was the observation that settled the argument between the Big Bang model and its steady-state rivals, because a hot early universe predicted precisely such a residual glow, and a steady-state universe did not. In 1978, the Nobel Prize in Physics was awarded to Penzias and Wilson for the discovery. The Holmdel Horn itself, its usefulness for cutting-edge work long since ended, was designated a National Historic Landmark 10 years after that, and it still stands where they left it, an aluminium relic of an accidental afternoon that turned a hiss into a message. The message, once received, had to be read more carefully, and for that new instruments were built. In November of 1989, NASA launched the Cosmic Background Explorer, known as COBE, into orbit. Its job was to measure the microwave sky with the kind of precision that a ground-based antenna could never achieve, because the atmosphere itself contributes noise no matter how clean the electronics are. COBE returned two extraordinary results. It confirmed that the spectrum of the microwave background was, to exquisite accuracy, that of a black body at just under 3 degrees, the signature of pure thermal glow, exactly as the Big Bang model required. And then, a few years later, in 1992, it detected the first faint temperature fluctuations across the sky, the tiny irregularities that would later grow into the great filaments of galaxies. Its successor, the Wilkinson Microwave Anisotropy Probe, launched at the end of June in 2001, took those fluctuations and sharpened them into a map fine enough to read the composition and age and geometry of the cosmos out of the patterns. And then, in May of 2009, the European Space Agency launched the Planck satellite, which spent more than 4 years drawing the finest map of the microwave background yet made, before its instruments were shut down in the autumn of 2013. Every one of those missions was, in a sense, a careful listening, an attempt to hear more clearly the faint uniform hiss that Penzias and Wilson had first stumbled into on a horn in New Jersey. The temperature they refined again and again was about 2.725 degrees above absolute zero. The photograph they resolved, again and again, was of a cosmos as it had been 380,000 years after its beginning, before there were stars, before there were galaxies, before there was anything one could point at with a finger and call an object. It is the oldest thing we can see. It is older than every galaxy and every deep field. It is older than every quasar, older than every element heavier than helium, older than any structure at all. And it is, right now, still arriving. Every square inch of sky, in every direction, is faintly warm with it. If you turn on a television set that has no signal, the old analog kind in the days when static was a familiar picture, a small fraction of the snow you would see was the microwave background arriving at your antenna. It is the most ambient thing in the universe. It is present in every room, on every mountaintop, at the bottom of every ocean. It has been present for as long as there has been anywhere to be present. It is the closest thing the cosmos has to a permanent feature. And yet, if the calculation is honoured, it is not permanent. It is fading. Every year, as the universe expands, every photon of that ancient glow has its wavelength stretched a little longer, its energy a little lower, its temperature a little cooler. The red shifting that began in the first free moment after the fog cleared has never stopped. It is happening now. It has cooled the microwave background from the incandescent heat of its release to the near-freezing whisper we detect today, and it will keep cooling. In some tens of billions of years, the wavelengths will have lengthened enough that no receiver of reasonable size could catch them. In some hundreds of billions of years, they will have stretched past any conceivable detector at all. The photograph will still be there, in the sense that the photons will still be somewhere, still travelling, still red-shifted, but they will be undetectable. The oldest message the universe ever sent will have arrived at a place beyond the reach of any envelope. It will fall silent in the same way the distant galaxies are falling silent, not by ceasing to exist, but by receding, in wavelength this time rather than in space, into a register that no instrument can any longer read. This is what Krauss and Scherer's astronomer, 100 billion years from now, will find missing when she sweeps her radio dishes across the empty sky. Not just the galaxies, not just the redshifts of the galaxies, the glow itself, the last relic of the early universe. The one thing that had been arriving from every direction since before there was anything else to arrive. It will have thinned past the point of detection, and there will be no way for her to know it was ever there. She will build her theories on a sky that has quietly mailed its last letter and closed the post office behind it. It is worth trying, just once, to feel the size of that. The microwave sky is not a distant thing. It is here. It is passing through the room you're in as these words are being read. It has been passing through every room, every landscape, every atmosphere, every ocean floor for the entire lifetime of the Earth, and for the entire lifetime of everything that came before the Earth. It is the ambient temperature of the universe itself, and it is the last audible echo of the moment the universe first became transparent to its own light. And it too is on the schedule. Not tonight, not in any human lifetime, not in any civilizational lifetime that could be seriously imagined, but on the timescale on which Lambda works, on the timescale that governs the closing of the fences already drawn. The microwave background is a fading thing. It is a message that is still being delivered, and will be delivered for a long time, and will one day cease to be delivered at all. And so the picture begins to settle into a shape one can hold. There is the great outer sphere of the scene, at 46 billion light-years, filled with galaxies whose old light is still arriving. There is the smaller inner sphere of the reachable, at 16, containing the small share of them any signal of ours could ever cross. There is the ambient glow, older than all of them, faintly present in every direction, cooling as it goes. And there is the fact, quiet and unarguable, that all of this is in motion, that the fences are moving and the glow is fading, and the golden age of illegibility we happen to inhabit is not a permanent feature of the cosmos, but a passing one. It is a room whose walls are drifting outward, and whose light is dimming, and we are in it tonight, with the lamp still on. There is one more thing to be said, before the story turns to what remains inside the 16, to the small local company of galaxies that will still be with us when all the rest have gone. And it is this: the loss that Krauss and Scherer described is not a loss of matter. Nothing that exists tonight will cease to exist. The distant galaxies will not blink out. The microwave photons will not vanish. Everything that is out there will still be out there. What will be lost is the exchange. The ability to send a signal, to receive one, to be witnessed and to witness, to know that the other is there and to be known in return. What will remain is the physical fact of the cosmos, unaltered, indifferent, going on. What will fall silent is the conversation, and that in the end is the register in which the whole of this story has been asking to be heard. The sky is not going anywhere, but the conversation is closing, one direction at a time, and it is closing while we watch. There is a smaller, quieter story woven through all of this, and it begins with the one exception the universe seems willing to grant us. Amid all the severance, amid the vast, slow work of the fences closing on every side, there is a single small enclosure that will not open, a single set of relationships the expansion is not permitted to touch. It has a name so plain that it sounds like a note in a ledger rather than a piece of cosmology. It is called the local group. It is the neighbourhood the Milky Way lives in, and it is the only neighbourhood it will ever have. The term itself was given by Edwin Hubble, the same man who first read the recession out of the redshifts and who spent his working life at the eyepiece on Mount Wilson, looking at the very galaxies that were, without anyone quite realising it, running away. He noticed that a small handful of nearby galaxies did not seem to be participating in the general flight. They were close. They were bound to one another by their mutual gravity, and their motions were governed by that binding rather than by the outward pressure of the cosmos. He called this small society the local group, and the name has stuck ever since, unassuming and accurate, describing exactly what it is: a group and local. The membership varies with the counting because the smallest members are dim and often hide in the glare of the larger ones or behind the dust of the Milky Way's own disk, but the number generally settled on is somewhere around 50, and some more recent tallies push it well past that as fainter dwarf companions are found. What matters is not the precise count but the architecture. Two great spirals dominate the arrangement, and everything else is a satellite of one or the other, or a smaller wanderer moving in the shared gravitational bowl the two of them make between themselves. One of the great spirals is the Milky Way, the other is Andromeda. The whole society is spread across a diameter of roughly 10 million light-years, which is a distance so small in cosmological terms that it barely registers on the scales this story has been using. 10 million light-years is a step. It is a room compared to a continent. It is less than 1/100th of the distance to the cluster of Abell 2029, and it is a rounding error against the 16 billion light-years of the reachable sphere. But this small span is the entire estate that gravity has been able to defend against the expansion, and it is the whole of the territory that will remain to any observer here after the long work of severance is done. Andromeda sits about 2.5 million light-years away, and it is, in the strictest sense, our neighbour. Under a dark sky, in autumn, it can be seen without a telescope. It is a smudge of light near the constellation of its name, and it is the most distant object the unaided human eye can casually take in, and every photon that reaches nigh from it left the galaxy before there were any human eyes to receive it. It is the largest single body in the local group, larger than the Milky Way itself by most reckonings, and it is moving toward us. Its radial velocity is about 110 kilometers per second, which is a briskness on human scales and a crawl on cosmological ones, and the direction of that motion is not away but in. Andromeda, alone among the great galaxies of the sky, is not receding. It is approaching. The reason is straightforward, though it took a long time to see clearly. The expansion of space is a global effect, but gravity is a local one, and inside a gravitationally bound system, the pull between masses simply overrides the stretching of the space between them. The local group holds itself together. Andromeda and the Milky Way have been falling toward each other since long before the acceleration began to matter, and they will keep falling toward each other for as long as the falling takes, which turns out to be a very particular length of time. Careful measurements of Andromeda's sideways motion, first attempted with the Hubble Space Telescope, and later refined with data from the Gaia spacecraft, have narrowed the arithmetic to a projection that can be stated in a single sentence. In about 4.5 billion years, Andromeda will meet the Milky Way, and the two galaxies will begin to merge. That is the same order of time as the age of the Earth beneath the reader's feet. It is the same order of time as the remaining lifetime of the Sun in something like its present form. It is not a symbolic timescale but a physical one, and it is unfolding. The word collide is the one usually reached for, and the word does honest work if it is understood carefully. What is meant is not the collision of individual stars. The distances between stars inside a galaxy are so enormous, relative to the sizes of the stars themselves, that when two galaxies pass through each other, almost no single star ever strikes another. The Sun will most likely never come within a light year of another star during the entire event. What collides is not the matter, but the geometry. The two spiral disks drawn together by their mutual gravity will pass into each other and around each other, and their shapes will unravel and rearrange under the influence of the encounter, and after many turns and many passes the two will settle into a single body. The gas clouds inside them will compress and ignite new generations of stars. The spiral arms will be lost. What emerges over hundreds of millions of years will be a large, smooth, elliptical galaxy, spherical or lens-shaped in profile, containing the combined populations of both original disks and belonging to no one of them any longer. It has been given, half seriously, a portmanteau name: Milkomeda, Milkdromeda. Neither is elegant. Both have the honest awkwardness of a compound built from two things that used to be separate and are now the same. Whichever name is used, the object being named is the future home of every star currently belonging to either galaxy, and it is the last major structural event the Milky Way will ever participate in. There will be no third partner. There will be no successor merger with some distant giant drawn in from the general field. The general field will, by then, already be receding beyond reach. The other members of the local group, the smaller spirals and dwarfs, will fall in and be absorbed on their own schedules, and the merged elliptical will eat quietly through its inheritance until the local sky is a single body with a single history, and then, on a longer clock, all of the other things visible tonight will have gone. That is the picture worth sitting with. A single galaxy, formed of what used to be two, gravitationally isolated, looking out into a darkness that no longer contains any visible companion. Not a lonely galaxy in the sense of being unhappy, because a galaxy does not know what it is, and to speak of it as knowing anything is only a manner of speaking, but a solitary one in the strict physical sense, the only structure in its horizon. The observers inside such a galaxy, if any exist, will see the stars of their own island, and the tenuous glow of the diffuse gas around it, and beyond that a sky that is dark in a way our sky has never been. The local group is the exception to the story of Severance. It is also the last exception. Everything else, in the end, is on the other side of a horizon that has already begun to close. And so we come to the sentence this story has been circling since the very beginning, and it is worth saying it in the plainest form the language allows. The universe is not passively drifting apart. It is actively severing itself. Every second that passes, a certain number of galaxies which were reachable a moment ago are reachable no longer. Their number is not small. On the accounting used in the earlier parts of this night, something like 160 billion stars per year cross the threshold into permanent unreachability, and that figure is not a projection into some distant epoch, but a description of what is happening now, tonight, while the sky in the window is doing what a sky does, which is to look still. The stillness of the sky is one of the great courtesies the cosmos extends to a body that lives for less than a century. It looks unchanging. The constellations that were named by shepherds and by scribes in cultures that have long since dissolved into other cultures are, for practical purposes, the same constellations that appear over a house tonight. The Milky Way itself is the same soft river across the summer sky that any ancestor would have recognized. The great galaxies just outside the window of the naked eye have been in their apparent places for the whole of recorded history. Nothing looks like it is running. Nothing looks like it is closing. And yet the arithmetic is unambiguous, and the arithmetic says that the closing is what is happening in every direction at once, at a rate that cannot be seen because it is written in the geometry of the space itself, rather than in the position of any object. The fraction of the observable universe that any signal we send tonight could ever reach is smaller than the fraction that could have been reached by a signal sent yesterday. That difference is small on any single day. It is not zero, and it accumulates. Whatever fraction was reachable when the first steady human eyes turned to the sky, whatever fraction was reachable when Slipher pointed his spectrograph at the Andromeda Nebula in 1912, whatever fraction was reachable when Hubble noticed the pattern in the redshifts and drew his line, whatever fraction was reachable on the morning in 1998 when the two supernova teams first admitted to themselves what their numbers were saying, every one of those fractions was larger than the fraction that remains tonight. The severance has been running the whole time. The window through which any two parts of the cosmos can still speak to one another has been narrowing while the astronomers who first learned to describe it lived and worked and slept and died. It is narrowing while these words are being read. There is a temptation, when a sentence of that kind lands, to reach for a technological escape. Perhaps a future civilization will find a way. Perhaps some engine, some trick of physics, some yet unimagined route through the geometry of space will restore the lost fraction. The honest answer, and it is the answer this story is held to from the first, is that no such trick is anywhere in the physics as it currently stands. The horizon at 16 billion light-years is not a limit of engineering. It is a limit of causal contact set by the expansion itself. A signal launched from Earth tonight, moving at exactly the speed of light and never slowing, would still fail to reach a galaxy just beyond that boundary, because the space between here and there would grow faster than the signal could cross it. There is nothing to build. There is nothing to invent. The fraction that is gone in the same sense that a message sent to a moment that has already passed is gone. The target has moved into a place from which no reply can come, and it went there while nobody was looking. And still the light is real. That is the part of the story that must be permitted to sit for a moment before the next thing is said. The galaxies out there are real galaxies. The image of Abell 2029 that opened this long night on the mountain in Hawaii was a real image made by real photons that had crossed a real distance to arrive at a real detector. The Hubble Deep Field is real. The Ultra Deep Field is real. Every point of light in those photographs corresponds to something that existed, that emitted, that turned starlight outward across space. What is not real, or what is no longer real, is the possibility of ever answering. The photons are the last dispatch from a place that has already passed out of our reach. We can see them, we can measure them, we can name them and catalogue them and classify them and write papers about them for as many generations as there are astronomers to do the writing. But we cannot cross to them, and we cannot signal them, and no message we might compose will ever be received, however patient the writing and however long the wait. The sky's a record. The record is precise, and the record is of a country we can no longer visit. There is a detail here that is easy to pass over. This closing is not scheduled for a future epoch. It is not a feature of some distant era one can safely leave to the imagination of one's descendants. It is a feature of the present, and it is quantifiable in the present, and the number changes while any given sentence is being spoken. The severance is not something we are approaching. It is something we are inside of, and it has been going on for as long as dark energy has been at work, which is to say for something like 6 billion years, and it will go on for as long as the universe continues to expand in the manner it presently does, which is to say, indefinitely. The unreachable is not an outer wall. It is a tide coming in, and it is against that tide that the last of the great instruments have been built. The James Webb Space Telescope was launched on Christmas morning of the year 2021 from the coastal jungle of French Guiana on the last flight of an Ariane rocket carrying something of consequence, and it climbed out of the Earth's shadow and continued for a month until it arrived at the second Lagrange point, 1.5 million kilometers out, where the Sun's gravity and the Earth's gravity balance in a way that permits a fragile instrument to loiter cheaply for as long as its fuel allows. Its mirror is a hexagonal flower of gold-coated beryllium, 6.5 meters across. Its sun shield is a great diamond of thin membrane the size of a tennis court, cooling the mirror to a temperature at which the faintest infrared whispers from the deep past can be picked out against the ambient noise of the instrument itself. And with this arrangement, it has begun to see galaxies as they were 300 to 400 million years after the Big Bang, which is further back in cosmic history than any earlier eye has ever managed to look. And every one of those galaxies imaged at record depth is on the wrong side of the fence. The younger the galaxy imaged, the further away in space it lies, and the further away in space it lies, the further it is behind the event horizon that is already closed against us. The most breathtaking images returned from Webb, the fields packed with warm ancient light, the delicate arcs of gravitational lensing bending the pictures of galaxies behind clusters, are, almost without exception, pictures of places that no signal we can ever send could reach. The sharpest eye humanity has ever turned upon the cosmos is not, in the end, an eye that brings anything closer. It is an eye that confirms with unprecedented clarity that most of what it sees is already gone from us. Adam Rees, one of the 3 astronomers to whom the discovery of acceleration was awarded in the Nobel citation of 2011, has spoken often in the years since about what it feels like to have found this out. He is, by training and by temperament, a measurer of things. His current work concerns the small, stubborn disagreement between 2 ways of measuring how fast the universe is expanding, and the possibility that the disagreement points to a piece of physics not yet understood. But he has also, in the way that people who have looked at the largest available things sometimes do, spoken about what a picture like the deep fields actually shows. Tens of thousands of galaxies, some of them 1 trillion times fainter than the faintest thing an unaided eye can see, and all of them in a patch of sky so small that a single grain of sand held at arm's length would cover the whole of it. That image of the fingertip and the grain has become one of the standard ways of teaching what the depth of the sky actually is. It is worth pausing on it here, in the register the story has been holding, which is neither the register of triumph nor the register of despair, but the register of a fact honestly received. Because what the fingertip covers in that image is not empty, it is full. It is packed with the light of things that once were, arranged in the sky in the exact configurations gravity and expansion have given them, and the fullness of that patch is not exceptional. The whole sky is like that patch. Every patch of the whole sky, wherever the great telescopes have looked, has been like that patch. The universe has been extravagantly generous with visible things and extravagantly stingy with reachable ones. It has given us the sharpest eyes physics permits, and behind those eyes the arithmetic of the horizon has been running the whole time, moving the fences inward while the pictures are being taken. That is the shape of the achievement. That is what the greatest telescope humanity has ever built has confirmed. Not abundance, closure. And the closure is precise. It is not a metaphor. It is not a mood. It is a boundary that can be located to within a fraction of 1 billion light years, and it is at present a boundary of about 16. Inside it, the small local company. Outside it, everything else. And everything else is most of what there is. The sky is, in the strictest possible sense, a record of things we can see but cannot touch. The window is closing. It has been closing for as long as anyone has been looking, and it is closing now, and it will not stop. There is one more turn the story would like to take before the night moves on, and it is the turn back inward, toward the 16, toward the small enclosure that will hold, toward the neighbourhood that gravity has kept for us, and toward what it will mean in the deep future, and also, quietly tonight, to live in the one place the severance does not reach. It is worth trying just once to feel what the horizon actually is, not as a boundary in space, but as a boundary in the ordinary human sense of how one thing touches another. Consider, in the plainest terms, what we mean when we say that we are in relationship with something. We mean usually that we can reach it, and that it can reach us. We mean that a word spoken in one direction is answered, or could in principle be answered from the other. We mean a two-way road. Almost everything we ordinarily count as connection is built on the assumption of that road, and almost every sorrow we know is a road that has narrowed, or a road that has been closed, or a road that runs in only one direction now because the person at the far end is no longer able to walk it. That last kind of road is the one the cosmological horizon most resembles. It is the shape of a great many quieter losses in the ordinary human life, and it may be worth naming them, because the arithmetic of the sky is easier to hold when you have already held its smaller cousins in your own hands. The letters that arrive after the sender has died. The recorded voice on a machine that plays a message the caller cannot now update. The photograph on the wall of the grandfather, taken before you were born, whose light reaches you, still, across a gap that will not close. In each of these cases, the direction of the road is fixed, and the direction is inward, and the person at the far end cannot receive what you might wish to send. The relationship is not gone. It has become one-sided. It has become, in the strictest possible sense, a matter of what can be observed and not touched. And a life is very largely made of these. The horizon in the sky is that same shape, extended to the size of everything. The light reaches us. Our light does not reach back. The picture is available. The touch is not. And the honest thing to say about it, the thing worth sitting with before the story turns for the last time toward home, is that the picture is not a consolation prize. It is not what we get instead of the touch we wanted. It is its own thing, and it is not a small thing, and it is not a lesser thing. The universe has arranged matters so that a great deal of what exists can be seen, and only a little of it can be reached. And the seeing has been given to us anyway in astonishing quantity, without our having earned it. To call the seeing a substitute for the reaching is to misunderstand what the seeing is. There is a study published a few years ago in a journal of physics in which an astrophysicist and a neurosurgeon set the images side by side. On the one hand, the great web of galaxies, filaments and voids and clustered nodes, the map of everything the deep surveys have found. On the other, the network of neurons in a slice of the human cerebral cortex. The two images, at the scale they were shown, are difficult to tell apart. The paper made a modest claim, carefully qualified, about the statistical similarities of the two structures at certain scales, and it stopped short of any of the larger metaphysical inferences the picture invites. But the picture, once seen, is not easy to unsee. There is a resemblance between the largest known structure and the structure that does the knowing, and whether the resemblance is a coincidence of physics or a hint at something deeper, the fact of it is quietly extraordinary. The universe has, so far as anyone can demonstrate, produced observers exactly once. It has produced them here. It has produced them now in a window in which the full picture is still available to be observed, and it has arranged them in some small and structural way to resemble the very thing they are looking at. There is a particular detail from the physics of the horizon that has always struck those who study it as gentler than it has any right to be. When a distant galaxy approaches the boundary beyond which its signals can no longer reach us, we do not from our side ever quite see it cross. The light coming from it is stretched and stretched, its clocks appearing to slow, its final moments spreading out over longer and longer intervals of our time, until the last photons arrive so far apart and so far shifted toward the red that they can no longer be distinguished from the sky behind them. There is no snap. There is no farewell. There is a fading that thins into the background so smoothly that no observer, however patient, could point to the instant the crossing occurred. The galaxy does not vanish. It becomes indistinguishable from silence. The physics of the horizon has spared us at least the moment of the door closing. It has given us instead a slow forgetting, arranged by the geometry of space-time itself, in which the loss is real and the exit is quiet. The universe, in other words, is not cruel in the manner of its severances, it is only patient. The horizon does its work in the same register as almost every large fact in cosmology, which is the register of things happening so slowly and so evenly that no single moment ever feels like the decisive one, and no observation ever catches the transition in the act. This is why it is possible to speak of the closing window without any tone of alarm. Nothing about it is sudden. Nothing about it demands anything from us. It is happening at the pace of the universe, which is the only pace it knows how to move, and the pace is compatible with a life, and with a night, and with an hour spent under a sky. And so, on that hour, and on that sky. The turn back inward, which the story has been circling toward now for a long while, is not a retreat. It is not a shrinking of ambition to fit the disappointment of the arithmetic. It is a recognition that what remains inside the 16 billion light-years of the reachable sphere is not a scrap. It is a neighbourhood, and the neighbourhood is enormous, and it will hold. The local group in which our galaxy sits contains something on the order of 50 members spread across roughly 10 million light-years of space, and gravity has bound it to itself against the widening of everything else. When the last of the distant galaxies has thinned into the background, the local group will still be here, orbiting itself, its members drawn slowly together by the same force that keeps the ground under your feet. The severance stops at its edge. What is inside is not going anywhere the horizon can take it. That is the sky worth going outside for, not the vast catalogue of the unreachable, glorious as the catalogue is, but the small enclosure that will still be here when the catalogue has faded. And on a clear night, in a dark enough place, most of what your eyes can find is precisely inside that enclosure. The stars scattered across the vault of the sky are, without exception, our own galaxy's stars, near neighbours in the same slow wheel we are riding. The band of the Milky Way, when you can see it, is the disk of that wheel seen edge-on from the inside. The scattered clouds and blurs that older eyes have known and named across every human culture are, for the most part, features of our own galaxy or its immediate companions. All of it is inside the 16. All of it is on the near side of the door. And then, in one particular direction, on a moonless night in the autumn or the early winter of the northern sky, if the observer knows where to look, there is a small, faint smudge in the constellation the ancients named for a chained princess. It does not look to the naked eye like much. It looks like a piece of the sky slightly more given to light than the sky around it. A soft grey patch about the size of the full moon, easy to miss and easy, once seen, to remember. That patch is the Andromeda Galaxy. It is the most distant thing the unaided human eye can find. Its light, when it arrives at the back of the observer's eye, has been travelling for about 2.5 million years, which is to say that it left its home at roughly the time the first members of our own genus were learning to walk upright on the plains of Africa, and it has been travelling steadily ever since, through the dark between two spirals, to arrive, at last, at the retina of a person standing outside on a particular night, looking up. That is a relationship. It is not the two-way relationship of a conversation. It is not a road that runs in both directions. But it is not nothing, and it is not a substitute for something better. It is the deepest looking a pair of unaided eyes can do, and the light it brings has been on the road since before there were eyes on Earth to receive it, and the galaxy it comes from is one of the two great members of the small company gravity has given us. Andromeda is coming closer. It is falling toward us at something over 100 kilometers a second, and in a few billion years, it and our own galaxy will begin the long, slow merger that will end with the two spirals folded together into a single elliptical shape. The horizon that is closing around the rest of the universe does not touch this. Inside the enclosure, the two largest members of the local group are drawing together. Inside the enclosure, gravity has arranged a future. There is instruction in that, and the instruction is very simple. Go outside, wait for your eyes to darken, let the small stars come in first, and then the larger ones, and then the dust of the galactic band if the sky's clean enough to show it. Find, if the season allows, the small faint smudge in the direction of the chained princess, and hold your gaze on it for a while and think, if you like, about the age of the light landing on the back of your eye. That is a picture of a place that is coming toward us. That is a picture of one of the 50 or so neighbours that will still be here when the far galaxies have all faded from the record. That is the reachable sky, and it is not a small thing. The rest of the sky, the wider sky, the sky that reaches out to the 16 and beyond it to the 46, is worth looking at too, and it is worth loving in the exact register it deserves, which is the register of a great and irrecoverable gift. The deep fields exist, the images have been taken, the catalogue of what was, and of where it was when its light left, has been assembled with a precision that the astronomers of a century ago could not have imagined. All of that is on the record now, and the record will outlast the light that made it. Whatever else the future does to the sky, it cannot take back what has already been seen, and cannot unmake the archive of what has already been measured. Someone, in a few billion years, sitting in the merged elliptical galaxy that our two spirals will have become, may still have access to the images that were taken during this brief legible window, and may still know from those images that there was once a wider universe out there, before the horizon quietly closed the view. The knowledge, once held, does not have to be lost with the seeing, and this is the strange, small, unlikely honour of being alive now. Not first, and not last, and not in the middle, but at the one moment in the history of everything when the full picture is still available to be seen and is still available to be understood. Before this moment, the mathematics did not yet exist to describe what the light was showing. Later than this moment, in the long thinning of the far future, the light itself will no longer be there to be described. In between, for a window that is as a small fraction of the total age of the universe and a very small fraction of its remaining life, the picture and the understanding are both in the room at the same time. That is now. That is this century and the ones on either side of it, and the small handful of centuries in which the deep fields will still be taken, and the surveys will still be extended, and the maps will still be drawn. It is a golden age, in the exact sense the physicists have used the phrase. It is the age in which the universe is legible, and the readers of it are here. Not somewhere else. Not at some other time. Here, on this small blue world in the outskirts of a spiral galaxy in the local group, in the one place the severance does not reach, during the one interval in which the picture is still whole. The universe has done a very large amount of work, over a very long stretch of time, to arrive at a moment in which it can be looked at by something that knows what it is looking at. It has produced the observers exactly once. It has produced them in a window that will not stay open, and it has produced them in time. That is enough. That is more than enough. The record is still playing. The sky is still full. The neighbourhood is still ours. The Andromeda smudge is still findable by an unaided eye on a dark enough night in the right direction. The deep fields are still on the archive servers, bruisable by anyone with a screen and a little patience, and the tens of thousands of galaxies inside each grain-sized patch of them are still, for all their unreachability, ours to look at. The window is closing, but it is not closed, and what happens inside a closing window, while the light is still coming through, is not less precious for the closing. It is more precious. It is precious in the exact way a season is precious, or a childhood, or an evening, or any of the other bounded things a life is made of. Losing the far sky is not the same as losing the sky. It is still out there tonight, and if the weather is kind and the town lights not too near, and the moon not too full, some of it will be findable from a step outside a door. The Milky Way's band, arching over the roof, the scattered near neighbours in their old patient patterns, the small faint smudge in the direction of the chained princess, coming quietly toward us at 400,000 kilometres an hour, its light 2.5 million years on the road. Behind all of it, invisible tonight and invisible on any night, the great faint background of everything else, most of it already past the door that no signal we can send will ever cross, but all of it still, for now, still shining onto our sky, in the record the horizon has not yet finished editing. All of it, the reachable and the unreachable together, arriving at the back of an eye that knows, at least a little, what it is seeing. You are the universe's chance to see itself, not the only conceivable one in the whole of what might exist, but the only one on the record, in the only window where the record is complete. The looking is not a small thing to do. The looking is the thing. So look. Tonight, or on the next clear night, or on any night the sky will have you, step outside, let the dark come in, and take the few minutes the neighbourhood is asking for. What you see is what the horizon has left inside the door, and what the horizon has left inside the door is a great deal, and it is yours, and it is still here. Thank you for travelling out to the edge of everything with me tonight. Keep looking up, take good care of one another, and good night.